Today in the workshop, we're working with Bluetooth on the ESP32. We'll see how to code servers and clients for Bluetooth Classic and BLE. We'll also learn how Bluetooth works and how to select the perfect ESP32 board for your Bluetooth project. It's a technology named after a king, so welcome to the workshop. Well, hello and welcome to the workshop, and today we are working with our old friend the ESP32, and the aspect of the ESP32 that we're going to be focusing on today is Bluetooth. Now, I don't need to introduce Bluetooth to you. I'm sure you have a number of Bluetooth devices. You may even be using Bluetooth devices to watch this video, a Bluetooth mouse or Bluetooth speakers perhaps. Bluetooth allows short-range connectivity between different computer peripherals. It can also be used for IoT devices, for wearable devices, for medical devices. There's a variety of things you can do with Bluetooth. And being able to connect the Bluetooth devices or to connect two ESP32s via Bluetooth can open up a number of doors and a number of new projects for you. Now, we're going to be dividing this video into two different sections today. The first section is going to be about Bluetooth, which is now called Bluetooth Classic. And the second section is about a newer form of Bluetooth, one that came out with version 4, and that is Bluetooth Low Energy, or BLE. And so basically we're going to learn all about these two different forms of communication. We're going to see how we can code the ESP32 to use these, and after watching today's video and looking at the accompanying article, you should be able to work with Bluetooth in your projects. So let's start by learning a bit about Bluetooth and BLE. Bluetooth and BLE are a series of communications protocols used to interlink computers, smartphones, tablets, and other peripherals. It finds use in Internet of Things applications, as well as in the creation of a personal area network of interconnected devices. Bluetooth was the brainchild of engineers at the Swedish firm Ericsson, who in 1994 set out to find a method of interconnecting computer devices wirelessly. In 1998, Ericsson joined with IBM, Nokia, and Toshiba to form the Bluetooth Special Interest Group, the group that sets all of the Bluetooth standards. Bluetooth itself was named for the 10th century King Harald Bluetooth Gormson, who also performed an interconnection. In his case, he connected the kingdoms of Denmark and Norway. Further respect is paid to the king in that the Nordic symbols for H and B, his initials, are the Bluetooth emblem. Since version 4, Bluetooth has been divided into two different categories. The first is the standard Bluetooth, now named Bluetooth Classic. It can also be called Bluetooth BREDR. This is for Basic Rate Enhanced Data Rate. Bluetooth Classic is used for high bandwidth applications such as streaming. The other form of Bluetooth is BLE, or Bluetooth Low Energy. This was originally called Bluetooth Smart. This is not compatible at all with Bluetooth Classic. The main advantage of BLE is its very low power consumption, making it useful for IoT devices and for wearable devices. Bluetooth Classic operates on the unlicensed 2.4 GHz industrial, scientific, medical band. Bluetooth Low Energy also operates on the 2.4 GHz ISM band. In Bluetooth Classic, the band is divided into 79 channels. In Bluetooth Low Energy, it's divided into 40 channels. Bluetooth Classic has a 1 MHz spacing between channel, whereas Bluetooth Low Energy has a 2 MHz channel spacing. In Bluetooth Classic, 32 of the channels are used for discovery. Bluetooth devices signal on all 32 channels. Bluetooth devices also scan constantly for other Bluetooth devices. In Bluetooth Low Energy, only 3 of the channels are used for discovery. These are called the primary advertising channels. Bluetooth Low Energy devices do not continually advertise. Instead, they advertise in intervals in order to save power. Pairing in Bluetooth Classic is initiated manually. Bluetooth Classic devices share a secret link key. This key can be established with a PIN or a Secure Simple Pairing SSP. Bluetooth Low Energy uses bonding for trusted connections between devices. Devices share a long-term key, and this eliminates the need for constant pairing. Protocols include JustWorks, Passkey, and OOB. In Bluetooth Classic, there is a continuous connection between devices. Bluetooth profiles are used to determine the interaction between devices, and we'll be taking a closer look at profiles in a bit. Bluetooth Classic will allow for data transmission and streaming. Bluetooth Low Energy, on the other hand, uses an intermittent connection to save power. It uses one profile called the Generic Attribute Profile, or GAT. BLE makes use of services and characteristics, and we'll be dealing with these later in this video. Bluetooth Classic is suitable for high-speed data applications. It's good for applications where you need continuous data, such as streaming. It also exhibits a very low latency, which is useful for audio applications. Bluetooth Low Energy's main feature is its very low power. Some devices can operate a year or more on a single battery. BLE is best used for short data bursts as opposed to continuous data. BLE devices can also be configured in a broadcast or mesh configuration. Today we'll be working with the Espressif ESP32, a microcontroller that supports both Bluetooth Classic and BLE. The ESP32 is an inexpensive and highly available microcontroller. It has multiple I/O ports, including analog and digital ports. It also supports programming in C++ or in MicroPython for BLE only. Internally, the ESP32 has one 2.4 GHz radio module. This module works on the industrial, scientific, and medical band from 2.402 to 2.480 GHz. The ESP32 contains a Bluetooth controller and baseband. It also contains a Wi-Fi media access controller and baseband. The ESP32 has a coexistence mechanism that can allow you to build applications that use both Bluetooth and Wi-Fi. If you wish to make use of the coexistence mechanism, you'll require the ESP Integrated Development Framework to develop with it. Today we'll be using the Arduino IDE to work with Bluetooth and BLE on the ESP32. So let's get going. And here are a selection of ESP32 modules that you could use for some of your Bluetooth experiments. Now you'll note there's quite a variety of modules here, and this is just a small sampling of things you can get. You'll see that we have modules that even have cameras and displays on them. There are some very tiny boards, and these are great for working on solderless breadboards, and they're also great for packing into small projects. I've also got some larger boards, and they've got a lot of I/O ports on them. You might find some of them a little wide for a standard solderless breadboard, but there are breadboards that can accommodate them, and they bring out all of the I/O ports in the ESP32. Now, you'll also notice a few of the boards have internal antennas, and some of them have external antennas, and for external antennas you can get tiny ones, and you can get very, very large ones, and of course you can boost the performance of your Bluetooth by putting an external antenna with a very good performance on it. But if you want something small, internal antennas are the way to go. Now, another thing about picking a board, though, is that not all ESP32s are the same, and not all of them have the same Bluetooth capabilities. So right now, let's go and take a look at the different versions of Bluetooth and the different capabilities of the different ESP32 models. There have been several revisions to the Bluetooth protocol since its inception in 1999. Bluetooth 1.0 was just for wireless data transfer and had no audio streaming functions. In 2001, Bluetooth 1.1 introduced audio functions intended for headsets. Bluetooth 1.2, introduced in 2003, provided support for stereo audio. Bluetooth 2.0, introduced in 2004, included functions for the audio-video remote control profile, allowing for multifunction Bluetooth remote controls. Bluetooth 2.1, which was introduced in 2007, contained many security enhancements and also introduced SSP, a method of not using a PIN number to mate Bluetooth devices. Bluetooth 3.0 was introduced in 2009, and its main feature was Bluetooth High Speed. This allowed for integration with an existing Wi-Fi network for improved file transfer. Of course, the Bluetooth 4 edition, which was introduced in 2010, brought out Bluetooth Low Energy, or BLE. The current level of Bluetooth that we'll be coding for is Bluetooth 5, which was introduced in 2016. It added increased range and faster data transfer, as well as improved audio quality. Bluetooth 5.2 was introduced in 2020, and it included Bluetooth LE audio, a method of sending audio over Bluetooth Low Energy. And the latest revision is Bluetooth 5.4, introduced in 2023. Now, when it comes to selecting an ESP32 chip, you should note that not every ESP32 supports the same level of Bluetooth. The original ESP32 supports Bluetooth up to level 4.2, and that includes BLE 4.2. The ESP32S series supports Bluetooth to level 5.0. It only supports BLE, it does not support Bluetooth Classic, and the ESP32S2 has no Bluetooth functions whatsoever. The ESP32C supports BLE only at Bluetooth level 5.0. The ESP32H series is also Bluetooth 5.0. It is BLE only, but it is BLE 5.3 certified. Note that the ESP32H2 does not have a Wi-Fi function. So armed with this knowledge, you should be able to choose an ESP32 chip for your Bluetooth application. Now, for one of the experiments we're going to be doing, you're going to need to have a serial Bluetooth terminal installed on either a phone or a tablet. And if you're using an Android device, I would recommend the Serial Bluetooth Terminal by Kai Moritz. As you can see, it gets very good ratings, 4.8 stars, and it's excellent for our application. Now, if you are on an iOS device, such as an iPad or an iPhone, I don't have one of those, so there's nothing I can recommend to you personally, but there are a few terminals on the Apple App Store. You might want to look at the Nordic RF one. It looks like it might be promising. If there's someone out there who knows of an iOS app, please put it down in the comment for everybody else. But you will need a terminal on your device to do one of our experiments. Okay, now that we know a little bit more about Bluetooth, it's time to start working with it. So we're going to dig out an ESP32 and we're going to start working with Bluetooth Classic, the original form of Bluetooth. Now, Bluetooth Classic is an excellent choice when you want to stream data or when you want to transfer large amounts of data. And what you need to understand in order to work with this properly is the use of different profiles and protocols. So we're going to cover that, and then we're going to take a look at the Bluetooth serial library, a library that comes with the ESP32 that makes transferring data with Bluetooth about as easy as working with the serial port. So let's go and learn a bit more about Bluetooth Classic and the ESP32. When we're working with Bluetooth, we'll be making use of the Bluetooth stack. The Bluetooth stack is software that implements all of the layers of the Bluetooth protocol. There are many different Bluetooth stacks available, and the ESP32 uses one called BlueDroid. BlueDroid is a popular open-source Bluetooth stack that is also used with Android devices. BlueDroid provides two different services, Bluetooth profiles and Bluetooth protocols. Let's check out a few Bluetooth profiles. These would include GAP, the Generic Access Profile. GAP is used for device discovery. It also manages all Bluetooth connections and security. A2DP is the Advanced Audio Distribution Profile. The term SNK is often included with this, and this means sync, a device that receives audio. A2DP manages the received audio stream. AVRCP is the Audio-Video Remote Control Profile. The CT included in the designation indicates it's used by a controller. This is used for sending commands such as play, pause, stop, volume control, etc. Now let's take a look at a few Bluetooth protocols. The first protocol we'll examine is L2CAP, or the Logical Link Control and Adaptation Protocol. This is kind of a traffic cop. It organizes all of the Bluetooth traffic. L2CAP is responsible for data transmission and the quality of data. SDP is the Service Discovery Protocol. SDP enables devices to advertise their services. For example, devices might advertise that they are capable of streaming or file transfer. AVDTP is the Audio-Video Distribution Transport Protocol. This is the protocol responsible for all audio and video transmission. And AVCTP is the Audio-Video Control Transport Protocol. This is the protocol used for control commands. You'll find this protocol used heavily in things such as speakers and media players. Today we'll be making use of the ESP32 Bluetooth serial library. This was installed in your Arduino IDE along with the ESP32 Boards Manager, and it's very easy to use. We'll start by including the library, of course, and then we'll define an object to represent the Bluetooth device. In this case, we call it serial BT. In setup, we'll start the ESP32 Bluetooth serial device with a begin command, and we'll provide a name. In this case, I provided my ESP32BT. This will become the name of my Bluetooth device, and of course, you can use any name you wish. Once we've done that, using the ESP32 Bluetooth serial library is very much like using the standard serial library. You'll note that you can do a write to send data to the connected device, available to check to see if data is available to read, and a read to read the incoming data from the incoming Bluetooth buffer. So now let's go over to the workbench and start working with the ESP32 Bluetooth serial library. Now the first Bluetooth Classic experiment that we're going to do is just a scan, and it's called the BT Classic Device Discovery. And this is a program that Espressif has provided for testing Bluetooth. Now remember, we're going to need to use this on an ESP32, not an ESP32S, ESP32C, or ESP32H, because we need one that supports classic Bluetooth. So you'll need an ESP32 module. We start the code off by including the Bluetooth serial library, and then we have a couple of sets of directives for the compiler over here, and this just checks to make certain that the hardware we've attached is capable of classic Bluetooth. So if you try to compile this for, let's say, an ESP32S3, it's going to fail down over here and it won't compile. So make certain you're using the right chip. Assuming we get past this point, we create a Bluetooth serial object called serial BT. Now we're going to be doing both an asynchronous and a synchronous scan. Now an async scan is a scan that operates in the background. It operates all the time and it doesn't block any tasks. If it finds something, it creates an interrupt. A synchronous scan, on the other hand, will only operate for a period of time that you tell it to run, and it'll block all other tasks. So when it's going, nothing else can go. And we're going to do both of these types of scans. Now the synchronous scan needs a timeout, and so that's what this is, the BT discover time. And these are just booleans that tell us which scan that we're actually operating. Now, this next thing here is a function called BT advertised device found, and this is what's called a callback function, and this is used with the asynchronous scan. Whenever it finds something, it's going to create an interrupt, and this is the callback routine it's going to call. And what it's going to do is it's just going to print to the serial monitor to let you know what it is we've discovered. So we'll go into the setup now, and we set up both the serial port and the serial Bluetooth port. And assuming we get past this point over here, the serial Bluetooth is working, so we'll just print to the serial monitor that the device is started. We're going to go and do our asynchronous scan first, or async scan. We're going to print that we're starting it, and this is the line that sets it off, BT discover async, and we give it the callback that we're going to be using, BT advertised device found. So every time it finds something, it's going to call that, which is going to print to the serial port. Now we print out that we're going to have the findings printed to the serial port. We go for 10 seconds and then we stop, because remember, the async one will keep going until you actually stop it. So we stop the async down over here and print its results. Then we go to the synchronous scan. Now the synchronous scan is the one that blocks all the other tasks. So we basically start it over here, and we pass to it the amount of time that we want to run. And so our discover time again is about 10 seconds. So if we have some results, we'll dump the results to the serial monitor, and then we'll end. And this ends the setup when we go into loop, and there's actually nothing to run in the loop because everything runs in setup. So let's load this up to an ESP32 and watch it work. And so we're about to try out our scan. I've got an ESP32 WROOM module connected to the computer, and I'm just going to give it a reboot so that we'll start it from scratch. And it's going to start the asynchronous scan, and it has found one device, and that's my phone over here. So you can see it's found the pixel down here, and it's given me the address, the RSSI. Now it's stopped the asynchronous, and it's starting the synchronous scan, and it should find the same thing. And there we go, it's found the same thing after 10 seconds. So we found the same device by doing two different types of scan, and you can of course decide which sort of a scan would be the most suitable for your application and use that in your program. Now for our next demonstration, we're going to create a simple Bluetooth client, and we're going to use it with a Bluetooth server. The Bluetooth server can be your phone or a tablet running a terminal application. The client code is pretty simple, and you can use it as the basis for your own code. Now we start off again by including the Bluetooth serial library as we did before, and we're going to give our client a name, and you can call it anything you want. I called mine ESP32 BT Client. Now the next two sets of lines are again the compiler checks to make certain that we're using the right type of hardware. So assuming we're using an ESP32 and not an S or a C or an H, we'll get through this section over here. And we create a Bluetooth serial object. Then we go into setup, and we'll start our serial monitor, and we'll also start the Bluetooth serial. So we'll pass a device name to it. Now this next line over here is commented out. You can uncomment it if you wish. After you have paired this with a device, the ESP32 is going to store that pairing information in PSRAM for use for future applications. Now if you want to delete that information from the PSRAM, you can uncomment this line over here, but normally we would leave it commented out. After that, we print the serial monitor to let it know that we're ready, and we go into the loop to do the actual operation. Now basically we're just communicating between the terminal and our serial monitor. So we're going to check our serial monitor to see if we've typed anything into it. And if there is something typed into it, we're going to do a serial Bluetooth write for what we're reading from the serial monitor. So we just pass it out to serial Bluetooth. And then we do the opposite. We check to see if we've got a message from the paired Bluetooth device. If we've got something available, we'll write that to the serial port. We'll put a really short delay down here and go and do the loop over again. So it's a pretty simple sketch. Let's load it up and watch it in action. Okay, so now let's demonstrate our serial Bluetooth. I've got the serial monitor set for my ESP32 board, and as you can see, it's started. I've got an ESP32 BT client has started and can be paired with Bluetooth. So let's go over to my phone, and first what we'll do is we will go to connected devices and try to pair a new device. And we'll look for new devices, and we do indeed see the ESP32 BT client, so we'll pair with that. And we'll pair it. Okay, so now that we're paired, let's go and open our serial terminal. Now the first thing we need to do in the terminal is connect to the actual device we've paired with, so we go to Devices, and we see the ESP32 BT client. So I've got that paired right now. And let's just type something up in the serial monitor. I'll hit enter. And if you can see, it's very tiny, but on the bottom of my client, I do indeed have hello there. I've already written the word hello into here. Let's send that off. And so I sent that up, and over here you can see I've got my hello back on my ESP32 serial monitor. And so we are exchanging text between the terminal and the ESP32. And of course this is just very basic, but you can use this as the basis for exchanging any type of data. If you want to send files, if you want to send control data to turn things on and off, you basically use the same principle. So now that we've worked with Bluetooth Classic, it's time to focus our attention on BLE, or Bluetooth Low Energy. And in order to work with and understand BLE correctly, you really need to know more about the Generic Attribute Protocol, or GATT. So we're going to dig deeper into GATT, and then we're going to take a look at the libraries that we can use with Bluetooth Low Energy and the ESP32. There are actually two profiles that we need to concern ourselves when working with BLE. GAP and GATT. GAP is the generic access profile, and we've looked at this already with Bluetooth. GAP controls things like the device advertising and establishing connections. It also takes care of security. Another thing performed by GAP is that it determines the network topology, and there are a couple of different topologies we can use with BLE devices. One topology involves a central device with a bit of intelligence, such as a smartphone or a computer. It attaches to a number of BLE peripheral devices, and it establishes a two-way communication. This is known as a connection-oriented topology, and the connection between a peripheral and the central device can also be referred to as a piconet. Another topology has our BLE device operating as a broadcaster. A number of external devices, such as smartphones, tablets, and computers, can be used as observers. There's only a one-way connection here. The broadcaster just sends out data but does not receive it. This is known as a connectionless protocol. Once we've established a connection, we use the Generic Attribute Profile, or GATT, to determine how the data is actually transferred. A GATT profile consists of one or more services. A service is a predefined collection of parameters which are called characteristics. The service will have its own unique numeric identifier, or UUID. A characteristic is a group of attributes. The characteristics are actually the data that is being transferred via BLE, and it has a number of components as well. The value component of the characteristic is the actual characteristic data. It can be a number, a string, or an array of bytes. The property component actually has three subcomponents: a handle, which is a 16-bit number used to access the characteristic, the characteristic's UUID, and the characteristic's permissions. Another component of the characteristic is the descriptor, and this contains additional information or configuration options for the characteristic. A GATT profile can consist of more than one service, and a service can have more than one characteristic. Here's an example of an actual service. This is the heart rate service. Note that it has three different characteristics, and the characteristics and the service all have a unique UUID. The Bluetooth Special Interest Group keeps a list of profiles, services, and characteristics, and you'll find a link to that list in the article accompanying this video. Official profiles use a 16-bit UUID. Manufacturers can also create custom services and characteristics, and those will use a 128-bit UUID. If you need to generate a UUID, you can go to the online UUID generator to create one. The ESP32 has a number of different libraries exclusively for working with BLE. The BLE device library initializes and configures the Bluetooth stack. The BLE Server library lets you set up a BLE server to which you can add services, characteristics, and descriptors. The BLE Client library performs the same function for a BLE client. The BLE Utilities library has a number of useful utilities for converting data types and for working with UUIDs. The BLE Scan library performs BLE scanning, and the BLE Advertised Device library will give you information regarding external advertised devices. So now let's go to the IDE and start working with Bluetooth Low Energy and the ESP32. Now for our first BLE example, we're going to create a BLE server. A BLE server needs to perform a number of different tasks. It needs to be able to advertise itself so the BLE clients can find it. It needs to create a service and at least one characteristic underneath the service, and it also needs to be able to have the client modify that characteristic by reading or writing to it. And this example from Espressif that we're going to look at does all three of these things. Now, it's actually a fairly simple bit of code. It starts off by including 3 different libraries, and then we're going to generate some UUIDs, both for our service and our characteristic. Now we're going to use the UUIDs that were provided to us, but if you want to create your own, you can go to this UUIDgenerator.net that they've got a link to over here and create your own IDs. Now we go into the setup and we're going to start our serial monitor and print that we're starting everything. Then we're going to initialize the BLE device, and this is actually the name that we're giving the BLE device. So you can give it some other name if you wish, but this initiates the BLE device. Then after that, we're going to create a BLE service. And so we're going to create the server with a service underneath it, and we're going to pass the service UUID to that service. Then we're going to create a characteristic, and these are the parameters for the characteristic. You can see we got the UUID, we've got a read property and a write property on it, so it can be read and written too. And then we're going to set the value of the characteristic, and it says hello world says Neil, considering the original author of the sketch was named Neil. If your name isn't Neil, you could change that if you wish. And then we're going to start our service. And then after that, we've got to do some advertising. So we're going to set up advertising over here. We're going to add the service UUID to the advertising and a couple of parameters, and then start advertising down there. And then after that, we'll print everything to the serial monitor, and we're basically done. Our server is working. So let's load this up and test it out. Now, there are a number of different methods I could use in order to test the BLE server. The first thing is to start it up and look in my serial monitor, where it tells me it has started the BLE work, and now I can read everything in my phone because the characteristic has been defined. Now, if I go over to my phone and go into the Bluetooth, I can hit pair a new device, and I notice in my available devices I have long name works now, and that's the silly name that we actually gave our BLE server. Now, the conventional way of testing this with a phone would be to use something like the NRF Connect app, which can connect to this and exchange data with the characteristic. But another way of doing it is to simply build a BLE client, and that's what we're going to do right now. Now, the final BLE example that we're going to look at is the BLE Client, which complements the server that we've just made. Now, the BLE Client needs to perform a couple of operations. It needs to scan for BLE services, that are BLE devices that offer services. It needs to connect to a specific service using the UUID, and it needs to read and write to a characteristic on that service, also using the UUID. And we're going to, of course, use the same UUIDs that we did for our BLE server. Now, we'll start off by including the BLE device library. Previous versions of this used the BLE scan, but it's no longer required. Then we're going to go and give our UUIDs, the service UUID and the characteristic UUID. Now, these are identical to the ones that we used on the server side. So if you have changed those for some reason, if you use the UUID generator to create your own, you'll need to make the changes here as well. Then we have a couple of Booleans that we set up just to define what parameters that we have, and a couple of characteristics that we define as well. And then we go to our first callback over here. Now, the notify callback is a function that is called automatically whenever the server sends a notification to say that the characteristic has changed. And so when we get that, we're going to go and grab the data and print it out. So that's what our callback does over here. Now, the next callback over here is a class callback, and it defines the actions to take when the client connects or disconnects. Now we're going to go to a function called connect to server, and it does a number of different things. I'm not going to go through all the code because there's quite a bit of it, but essentially this creates the BLE client. It connects it to the remote BLE server. It reads the services and characteristics. It reads the characteristics value, and it registers for notifications if the remote device allows for notifications. So you can go through all of that, and that's what's happening over here quite a bit. Here's the notifying down at the bottom here. And then after that, we have a my advertised device callbacks. This is a class callback, and it handles what to do whenever we discover new BLE devices. Now we're going to move on to the setup. We'll start off our serial monitor and print to it, and then we'll initialize the BLE device. We don't need to give it a name because we are a client. And we'll retrieve the scanner and callback that we want to use down over here. And so we'll set everything up and we'll go into the loop and we'll check to make sure we're connected. If we're connected to the server, we're going to print that we're connected to it, else we're going to print that we have not connected and we're going to just fail right at this point. If we have connected to the server, we're going to do something. We're going to get the time since boot, and we're going to do that with the millis command. The millis function takes the amount of milliseconds since the ESP32 has been booted. So we're going to get that, and we're going to create a new value for that. And we're going to use that to modify the characteristics. So we're going to do that within here. We're going to put a short delay onto that and go and do it over and over again. So there's a lot of code over here, but when you break it down, it's not too hard to understand. And if you want it broken down in great detail, the article accompanying this video on the DroneBotWorkshop.com website will do that for you. So now let's go and give this a test with our BLE server. Now for this demonstration, on the left side I have our server, and on the right side I have got the client, and I've got the client moved over so you can see what it's doing. It is incrementing indeed. Every second it is changing the characteristic value, and it gives it the time since boot, and this is the number of seconds since it is booted. Now on the server side, it just once again just says characteristic defined. Now you can read it in your phone. So these two are definitely communicating with one another, and again, it's a fairly simple demo, but this demo can be used as the basis for other code where you can create BLE devices, both clients and servers. So that concludes our look at Bluetooth and BLE with the ESP32. I hope that you enjoyed it, and if you need a bit more information or if you'd like to look deeper into the code that we used today, you'll find all of that in the article that accompanies this video on the DroneBotWorkshop.com website. Now, while you're on the website, if you haven't yet, please consider signing up for my newsletter. It's not a sales letter. It's just a way of getting in touch with you to let you know what's going on in the workshop and to tell you about the subject of upcoming videos. And of course, it's free to sign up for the newsletter. All I need is your email address. If you're in a signing up mood, I've got a few more things you can sign up for. The DroneBot Workshop Forum is a great place to go if you need help with your electronics projects or just want to chat electronics with a number of like-minded individuals. And it's free to sign up for the forum. There's details right below this video. And while you're in that signing up mood, how about subscribing to the YouTube channel? If you haven't done that yet, I make videos about things like the ESP32, microcontrollers, and electronics, and if you enjoyed this video, I'm sure you'll enjoy my other ones, and I'm planning on creating some more videos on ESP32 Bluetooth projects, and so if you want to see that, when you subscribe to the video by clicking on the red subscribe button, you'll also want to make sure to click on that bell notification, and that way you'll get notified every time that I make a new video. So until we meet the next time, please take good care of yourself, stay safe out there, and I will see you soon here in the DroneBot Workshop. Goodbye for now.